Hello, thanks for your interest in this work. My name is Kun-Ting Chen. Today I'll be talking about our work interactive visualizations of cyclical data on cylindrical Toroidal topologies. This is joint work with Dwyer and Marriott from Monash University and Benjamin Fred from the University of Edinburgh. We often see charts representing cycles of days and nights, seasons or years. Examples include average monthly rainfall in Bangkok, average number of births per month in UK, and hourly traffic flows over 24-hour periods in New York City. However, standard linear bar chart often represent cyclical data from January at the left end and December at the right end, or 1 a.m. at the left end and 11 p.m. at the right end. So a user may need to manually join the bars from December to January, or from 11 p.m. across the page to 1 a.m. This makes the inspection of the trend across the cards difficult. One common way to overcome this problem is to arrange cyclical data in polar representations. Polar visualization show time in a circle, allowing for continuous representations of trend and patterns in any part of a cyclical data. This no longer shows a visual card in the linear chart. However, existing literature found that polar charts generally are less effective than linear charts. For example, Warden and others compare human readability of time series data with daily patterns, finding that for low-level tasks such as locating extrema, comparing values within values, linear chart is faster than polar charts. Eden and others found that people make less error using linear charts compared with polar charts for trend identification tasks. However, there is no empirical evidence comparing readability of cyclical intervals split across the cards on bar charts. In this paper, we present novel interaction of linear and polar representation of cyclical data to work around their respective limitations. For linear charts, we present a technique to allow a user to drag the charts horizontally to look at time series data out of the box. By dragging the chart, a user can bring 11 p.m. and 1 a.m. together, while the wrapping is elsewhere in other hours. For polar representation, we implement a rotate gesture, so a user can rotate to bring the bar to the top or center bars for more aligned comparisons. Such rapid panning, we have not seen such panning applied to charts before, but it is inspired by Chen and others' recent results of promising comparison between interactive wrapping of Nolan diagrams and the standard unwrapped representations. In the following talk, I will describe the following steps to investigate readability of cyclic time series data and the effect of interactively wrapping the bar chart around its boundaries. First, I'll go over the rendering and interaction of the techniques tested. Second, I'll describe the control experiment of wrapped time series readability with 72 participants. 3. Inspired by the study results, I'll describe the design space which generalized the concept of interactive wrapping to wrappable visualizations. We implemented 4 chart types for the study: linear charts, polar charts, with and without interactions. We removed the tick marks, grid lines, and labels, so the visual comparison is purely based on the bar height. We use monochrome color as colors are found to make the comparisons between linear and polar charts negligible for time series studies. We recruited 72 participants through prolific crowdsourcing academic platforms. We used within subject design, so each participant went through the same set of trials, counterbalanced by the techniques. For our study trials, we used the real-world data sets from selected boroughs of New York City's hourly traffic flows over a 24-hour period between 2013 and 2016. First task is trend identification. We first show examples of highlighted sequence of bars that are continuously decreasing. Animated examples demonstrating inductive wrapping are given. Then, an identical example to the interactive wrapping is shown to the participant for them to try themselves. Then, we present examples where highlighted sequence of bars are continuously increasing. And finally, we show the examples where highlighted sequence of bars are neither continuous decreasing nor continuous increasing. Similarly, animated examples are given to participants, which demonstrate interactive wrapping. An identical example is provided for participants to try themselves. For polar charts, the setting is the same. The results indicate that for trend identification tasks, interactive bar chart, static polar, and inverted polar are significantly more accurate than static bar charts. More results and detailed statistics results can be found in our paper. The next task is pairwise single value comparison. We present examples showing that one of the bars is higher than the other. Animated examples are provided demonstrating the interactive wrapping. Analytical examples are provided for participants to try themselves. The setting is same for polar charts. The results indicate that for pairwise single value comparisons, interactive bar charts significantly outperform static polar, and interactive polar in terms of error. Detailed statistics results can be found in our paper. Inspired by the study results, we generalized the concept of interactive wrapping to wrappable data visualizations in 3 design dimensions: topology, projection, and panability. As we see previously, one-way wrapped visualization, such as cyclic time-series data, can be described as cylindrical. Side projection results in linear bar charts, while top projection results in polar bar charts. This example is a non-temporal data type. This Sankey diagram shows cyclic energy transfer in engines. Since it's cyclic in one vertical direction, it can be represented on a 2D cylinder. Cyclical data with 2 dimensions, such as average traffic volume by hour in horizontal axis and by day in vertical axis, can be represented on the torus topology. Torus wrapping allows us to see cyclical patterns across the day from 11 p.m. to 1 a.m. or across the week from Saturday to Monday. The same cyclic data can be represented on a polar chart. By top projecting a torus, a user can rotate the hour dimension and use panning to wrap the days. This allows the user to see a continuous representations of hours across days. Relational data such as networks can be represented on 2D tours. Chen and others found that interactive wrapping of network visualization significantly improved people's understanding about network structures. Overall, our study results indicate that interactive wrapping leads to significant improvements in error over static representations for trend and value comparisons. Polar representation is significantly faster in terms of error than static bar charts for trend task. Our design space shows that cylindrical topology are well suited to data that is cyclical in one dimension. Toroidal topology are useful for data that has two dimensions and for relational data. Our future work is to evaluate two-dimensional cyclic time series readability. Furthermore, we also evaluate non-temporal cyclic data types such as geographic maps or flow diagrams with cycles. We also explore practical usage of domain expert for domain experts. Thank you. We are happy to take any questions.